start. So if you have any questions, please type your questions into the text box. Section 9.5, graphical representations of functions. So let me tell you about the techniques of graphing. So the first technique is translations, where we have rigid translations where we move right, left, up, down, but we do not change the shape of the curve other than just moving it from one location to another. Reflections, where we will take the graph and we'll reflect it about a line or maybe a point, and the shape will stay the same, but it now is somehow reflected. Scaling. In this case, what we'll be doing is either compressing or expanding the graph in one direction, such as maybe in the X direction or in the Y direction. For rotations, that is for a later course. One of the techniques is rotations, but we'll talk about that in a later course. So let me give you some of the basic graphs for power functions. So suppose I have some coordinate system and I want to graph y equaling x to the n for n, an even integer. Greater than 0. In this case, the graph will look something like this. Let's do another graph. Again, we're going to be graphing y equaling x to the n. Suppose that n in this case is an odd integer. And suppose that n is greater than 1. And so in this case, the graph will look something like this. For the first graph, it is symmetric about the y-axis. For this graph, it'll be symmetric about the origin. To the graph of, again, y equaling x to the n. But in this case, let n equal 1. If you do that, then the sketch of the graph will just look like a straight line passing through the origin, having a 45-degree angle. Next. Suppose I want to graph y equaling x to the n, where n in this case is 0. In this case, it'll just be a horizontal line. And it'll pass through the point y equaling 1. Next, suppose I want to graph following. Suppose I want to graph y equaling x to the n. And in this case, I guess I'll have that n is an even integer, but let n, in this case, be negative. Okay. So if you do that, then the graph of it will look something like this. It should be symmetric about the y-axis. Suppose I want to graph. Again, y equaling x to the n, my power function, where in this case n is a odd integer. And suppose n here is less than 0. And so then the graph will look something like this. It'll be symmetric about the origin. Suppose I want to graph the following. Y equaling x to the n. Well, maybe I'll write 1 over n. Where n in this case is an even integer. And n is greater than 1. So it looks something like this. Next, suppose you want to graph. Y equaling x to the 1 over n. Where n is an odd integer. And n is greater than 1. In which case it'll look something like this. It'll be symmetric about the origin. Okay. Now, if you have y equaling x to other values of n, they'll look very similar. You just have to sort of merge these pictures. So for fractional exponents, they'll look like basically, they'll just sort of be the transition from each integer value to the next integer value. But of course, being sure that they're defined, so some branches may not be defined. The graph of the absolute value will just look like this. So this is the graph of absolute value of x. So that basically gives you the power functions and the absolute value. So that's, if you have a particular power function, well, you know how to graph it. You have to memorize. So my assumption is that you have memorized and you know how to graph any sort of power function. So if I give you a power function, you should know how to graph it. And then utilizing the fact that I'm going to give you these other techniques of graphing, then you should be able to graph most of the graphs that we're going to encounter in this course. There's a few graphs at the end that you won't know, but almost every uh, the, almost every function that we have looked at so far. Well, every function we've looked at so far, and a few more that we shall be seeing in the future. So let's recall the following. The zero of a function this is the same as the root of a polynomial. So if I'm talking about a function, then I'll call it the zero of a function. If I'm talking about a polynomial, call it the root of the polynomial. If I'm talking about a curve, I'll call it the x-intercept. So these are all the same thing. So if you recall, well, we're doing functions, so I'll call it a zero of a function. If you recall, how to find the x-intercept is you set y to 0 and solve for x. So to find a zero function, set y to 0 and solve for x. And that'll give you the 0 of your function. Okay, so let me give you translations, reflections. So first, let h, so for my notation, so let's do translations. And I'll just assume here, to make it nice and easy, that h is greater than 0 and k is greater than 0. And suppose I have some function y equal f of x, and somehow I've graphed this, and I want to figure out, well, how do I graph the translation of it? So suppose I have the following transformation. This will give us the following results. Okay, so suppose that x, instead of x, I write x minus h. The result is that I should translate right. I should translate the graph of y equal f of x right by h units. And so this is h units in the positive x direction. Okay. Next, suppose I have the following transformation. X. And instead of writing x, I write x plus h. In this case, I'll translate left by h units. So in other words, h units in the negative x direction. Next, suppose I had the following transformation. Oops. Y goes to y minus k. And so in this case, I'll translate the graph y equal f of x up by k units. In other words, k units in the positive y direction. Next, suppose I have the following transformation. Y goes to y plus k. Then I'll translate down by k units. So in other words, k units in the negative y direction. So again, notice math is backwards. So if you subtract k units, h units from x, then you go in the positive, you go h units in the positive x direction. If you add h, then you go in the negative x direction. If you subtract k from y, then you go in the positive y direction. If you add k to y, you go in the negative y direction. So notice that it's always the opposite. Let me do reflections about an axis. Okay, so suppose I have the following transformation. Suppose instead of x, I have negative x. So I'm going to replace x here by negative x. Well, if I do that, then I should just reflect about the y-axis. So if you replace x by negative x in the and you look at the graph of y equaling f of negative x, then you just reflect the graph of y equaling f of x about the y-axis. Next, if you replace y by negative y, then you just reflect the graph of y equal f of x about the x-axis. So again, note, if you negate the x, you reflect about y-axis. Negate the y, reflect about x-axis. So again, everything makes sense because math is backwards. So you do the exact opposite. Next, scaling. Let me suppose that a in this case is greater than 1. Easier to talk about it if I have that. So suppose I replace x by x over a. Then you should stretch the x-axis by a factor of a. So if I replace x by x over 2, then I would stretch the x-axis by a factor of 2, meaning I would double. I would double so the x-axis would be stretched by doubling it. It would be twice as long. Okay. Suppose replace x by ax, then I will compress the x-axis by the factor of a. So if I replace x by 2x, then what that means is I'm going to compress it by a factor of 2. So it's going to be basically squashed in half. Again, math is backwards, so it makes sense. If I replace y by y over a, then I'll stretch the y-axis. So that means I look at the graph of y equal f of x, and then I take that graph and I stretch the y-axis, and then that deformation of the graph of y equaling f of x will be the graph of y over a equaling f of x. So stretch the y-axis by a factor of a. And lastly, suppose I have y and replace y by ay. And so with that transformation, I'll just compress the y-axis by the factor of a. Okay. So I guess I'll just sort of note rotations will be discussed in Calc 2, Math 266. So well, obviously we don't do rotations in this course. We wait until Calc 2 to look at those. Okay, now actually we have sort of done this before. And so if I look at the graph of y equal x, okay, well, if I look at the graph of y equaling x, luckily we know that because I just told you to memorize it 5 minutes ago. And so this is just a line passing through the origin, having a 45-degree slope, meaning that if I go 1 unit in the x direction, oh, maybe I should make it red. 1 unit in the x direction, I go 1 unit in the y direction. Oh, okay. So now, let me perform the following scaling. So let's now do the following transformation. Or apply the following transformation. And so let's replace y by y over m. Okay. And so if I do that, then it says that I should scale the y-axis by stretching by a factor of m. Actually, I don't know if it's stretching or compressing because it depends on if m is greater than 1 or less than 1. So for the graph, of y equal x. Okay, so it says that if I want to look at the graph of, let's apply the transformation, y over m equal x, which is just y equal mx. If I multiply both sides of my equation by m, I'm assuming m here, of course, is not 0. Then I take the original graph here, and I stretch or compress the y-axis by a factor of m. Okay, so I'll be doing that. And so now the slope will somehow change. Of course, it could be, the slope could be going higher up or so it could be going up here at a steeper value or at a less value. But that's fine. But all I do know is that means that this line here that we had going up 1 no longer goes up 1. It's been stretched by a factor of m. So it now goes up m units. Oh, and well, we know what we call that. And so notice that, well, if m were greater than 1, then we would be expanding. If m were less than 1, then we would actually be compressing the x-axis. Here, I'm assuming that m is greater than 0, so that we haven't talked about reflections yet. But notice that this is just the fact that that's the slope. And so back in chapter 3, I guess, we called that scaling of the 45 degree line, the slope of the line. And so m, the slope of the line. So note that if m is less than 0, then replacing y by negative y yields a result. Yields the above graph. But with a negative slope. So if I just reflect about maybe I'll just put it in yellow or something. If I reflected about you can barely see that, but if I reflected about the uh, x-axis, then that would just, if I place y by negative y, I'd reflect about the x-axis, and that would just give us the same sort of thing, but now the slope would be going in what we would normally call a negative direction. It'd have a negative slope. So, thus, the transformation y going to negative y yields negative slopes. Well, slopes yields negative slopes. Okay. So now let's take the translation. So now apply the transformations. And so I'll actually apply two transformations. And so let's do x, and let's do, let's say x minus x1, and y, let's do y minus y1. Okay. And so to yield the graph of the line translated x1 units in the x direction and y1 units in the y direction. So thus x1, y1 is a point on the line and so the graph of, well, let's look at the transformed line. And so if I look at the transformed line, I've replaced, so the graph of y equal mx has been transformed to y minus y1 equal m x minus x1. It passes through a point x1, y1, and it has, say, slope of m. Back in chapter 3, we called this the point slope form for the equation of a line. And so, yes, that all makes sense. And so that's why back in chapter 3, we had all these weird signs of minuses and all that because we were doing a translation. So let's do on page 385. Problem number 6. G of x equals x squared plus 1. In exercises 1 through 26, sketch a graph of each function by hand and verify using a graphing calculator. Well, I guess I'll just sort of say, well, you could verify it, but I'll assume I'm correct. So what I'll do is I'll start with some sort of basic graph and transform it so I can get the graph of this function. So first off, let me replace g of x by y. Let me subtract 1 from both sides of my equation. So I get y minus y1 equals x squared. Oh, so this is just a translation of y equal x squared I'm subtracting 1 from y, so I should go in the positive y direction. So I should go up 1 unit. And so let's sketch a graph of this. So first off, let me sketch the graph of y equaling x squared. Maybe I'll do it in red. So this is the graph of y equaling x squared. And of course we know that because we have memorized all of our power functions. Now what I have to do here is I am going to have to translate this up by 1 unit. So I'm going to have to take every point on this graph and just move it up by 1 unit. And so let's do that. So it should look the same. Well, whatever. It should look, that's a little scraggly there. That's all kind of bad, but okay. And so now this is the graph of y equaling x squared plus 1. And so I've moved it up 1 unit. Let me do problem number 12. G of x equals 1 minus x cubed. Again, let's replace g of x. Oh, I guess I should say, well, and so let's replace g of x by 1 minus x cubed. G of x by y, so y equals 1 minus x cubed. Let me subtract 1 from both sides of my equation. So I get y minus 1 equals negative x cubed. Okay, so this says that, well, I should translate the graph of, well, y equaling negative x cubed. Let's see, I'm subtracting 1 from the y, so I should go up 1 unit. Next, I have y equal negative x cubed. So let me multiply both sides of my equation by negative 1. And so I get negative y equals x cubed. Oh, so that's a reflection. So I should reflect the graph of y equaling x cubed. Notice I've changed y to negative y, so I should reflect this about the x-axis. Okay, so now let's do that. So I'm going to have to first reflect about the x-axis and then translate up by 1. And so let's do that. Please note that when reading these transformations, you start at the bottom and go up. Okay, so if you have a whole bunch of series of transformations, you'll do the bottom one and then go to the top one. Okay, so let's sketch the graph of this. It's a little bit at a wrong angle there. Good enough, I guess. Okay, so let's first sketch. Maybe I'll do it in red. The graph of, well, y equals x cubed. Luckily, I know that because I just memorized how to graph all power functions. So that's the graph of y equals x cubed, and I want to reflect this about the x-axis. So I'm going to take the curve here, I'm going to reflect it about the x-axis. Oh, maybe I'll give it a green color. So once I've reflected about the x-axis, it should look something like that. Hmm. A little bit better. So it should look something like this. Okay, so this is the graph of negative y equal x cubed, or y equal negative x cubed, whatever you want to call it. So now let's translate this up by 1. And that will give me my curve that I want. And so, actually, let's do that. So it goes, okay, let's try that again. Okay, so okay. Good enough, I guess. And so this is the graph of y equaling, oops, 1 minus x cubed. So this dark black final line is the graph that we want. Let me do problem number 18. So when sketching graphs on the exam, I expect for you to show all these transformations, how you go from one to the next. So g of x equaling absolute x plus 1. Okay. So this is y equal absolute x plus 1. So this is just a translation of the graph y equal absolute value of x. And notice I'm adding 1 to x, so I should go in the negative x direction. The negative x direction is left. And so I should go left by 1. So let's sketch the graph of this. So the graph of the absolute value, well, it sort of looks like a V, I guess. So that's the graph of the absolute value. And now I want to go left by 1. So I'm going to have to take this guy here and go left by 1. So if I do that, then my graph should look something like, oh, gee, should look something like this. Okay, and so this is the graph of y equaling absolute x plus 1. Let me do problem number 2. F of x equals 3x minus 2. Of course, I know that this is just a line having slope 3 with y-intercept negative 2. Which is the original. So the line that we want to actually sketch, meaning g of x, is the black line. So this line here, the black guy, this is, so this line here, that's the answer. That's the sketch of this graph here, y equal g of x. Okay, so the very last black one is the correct, is the answer to the original problem. Okay, so that's the, could make it kind of dark here. Well, now it's getting messy, but so that's the answer that, yeah, so this is it. So these. Okay, so those are the answers. There. So now it looks more obvious because it's the really dark guy. So the one that I sort of sketched over several times. Now it doesn't look as nice because it's sort of sketched over 50 times, but that's the graph of the thing that we wanted. Okay, so let me do problem number 2. So let's replace f of x by y. Let me add 2 to both sides of my equation. So y plus 2 equals 3x. Okay, so the transformation here is I'm going to uh, transform y to y plus 2. So I'm going to be translating. So it's a translation of y equaling 3x. And this is going to be, well, it's in the y direction. I'm adding 2 to the y direction. So I'm going to be going in the negative y direction, which is down 2. Next, let me divide both sides of my equation by 3. And so this is just y over 3 equals x. Aha. So let's stretch. So this is going to be a scaling. So I'm going to stretch the y-axis by a factor of 3 for the curve y equaling x. Okay, so let's do this. So first start out with y equal x. Now I'm going to stretch by a factor of 3. So this is going to stretch. So if I went 1 unit, now I'm going to go 3 units in x. So instead of going, say, over 1 up 1, I'm going to go over 1 up 3 because this 1 here all of a sudden goes, this 1 here would go all of a sudden to 3. And so let's do green. I'll do that green. Okay, so now it's going to be stretched by a factor of 3. It's going to be much steeper. Okay. So, oh, and this is, I guess I should have said 3 here. So I've stretched the y-axis by a factor of 3. So now this is the graph of y equaling 3x, or y over 3 equal x. Now, let's translate this going down 2 units. So let's go down by 2 units. Oh, maybe I'll make this into a slightly bigger point. So now I'll go down 2 units. There. So now you can definitely see it's much thicker. Okay, so give me back. So now I've gone down, oops, I've gone down here by 2 units. And so this is now, this 0 goes to -2. Okay, and that's the graph of y equaling 3x minus 2. Okay, basically what we knew from chapter 2. Or chapter 3. Okay, let me do problem number 16. Oops, wrong color. So problem number 16. G of x equals radical x plus 1. And so y equals radical x plus 1. Yes. Yeah, so the black line, yes, is the original. So the one that's much darker than everyone else is the graph of what we wanted. Okay. So in this case, I'm just, yeah, the 3x minus 2, correct. So in this case, I'm just replacing x by x plus 1. So I'm going to translate. So this is a translation, a rigid translation of y equaling the square root of x. And this is, again, I'm adding 1 to x, so that means I'm going 1 in the negative x direction, which is to the left by 1 unit. So let's sketch a graph of this. So the graph of the square root of x, well, we know that. That's the same as actually, if I looked at the graph of x squared and just interchanged x and y, it's the graph of that. It turns out the square root is just the inverse function for the square. But of course, we have to restrict our domain, so it actually is just half of it. So that's the sketch of the graph y equaling square root of x. Now I'm going to translate this left by 1 unit. And so I get that. Oh, I guess I should make it into a bigger guy. So it looks something like this. And so that's a graph of y equaling radical x plus 1. Okay. Okay, so I guess that finishes off section 9.5. Okay, so let me save this. So here I'm gonna actually quit, exit, and then I'll come back in about 5 minutes so that I can tape the other section. Bye. Oh, so everyone's got to. Oh, that's right. Actually, everyone's got to leave, and then so cancel that. Sorry about that. Actually, everyone's got to leave first. So let's stop.